Model theory is where mathematical logic meets algebra. It is the study of mathematical structures through formal languages. Think of it as using the precision of logic to understand the world of mathematical objects. Let's start with the basics of formal languages. These are the building blocks of model theory. The basic components include variables, which are represented by letters like x, y, and z. These act as placeholders. Then we have constants denoted as C1, C2, and so on. These represent specific, fixed elements. Function symbols, such as f and g, represent functions that take inputs and produce outputs. Relation symbols, such as r and s, represent relationships between elements. An example formula is, for all x, there exists y such that r of x and y. This can be read as, for all x, there exists a y such that r of x and y holds. A mathematical structure is the concrete world in which our formal language lives. A structure consists of a domain, which is a set of objects we're interested in. It also includes interpretations, which are the meanings we assign to function and relation symbols within that domain. Also, constants, which are specific elements of the domain that we single out. For example, consider a group structure denoted as G equals open parenthesis G, the set, the operation, and E close parenthesis. Here G is the underlying set of the group. The circle symbol represents a binary operation that combines two elements, and E is the identity element. The satisfaction relation defines when a structure satisfies a formula. In other words, when a formula is true in the structure. For a formula to be satisfied, all variables must be properly interpreted within the structure, and the relation specified in the formula must hold as described. The notation for this is, A satisfies phi, which is read as, structure A satisfies formula phi, meaning phi is true in A. Elementary equivalence is a key concept that allows us to compare different structures. Two structures are elementarily equivalent if they satisfy the same first-order sentences. This means they share the same logical properties, at least as far as first-order logic can express. We denote elementary equivalence as A is elementarily equivalent to B. This means for every sentence phi, A satisfies phi if and only if B satisfies phi. The compactness theorem is a fundamental result in model theory. It states that if every finite subset of a set of sentences has a model, then the entire set has a model. This means that if you can find a structure that satisfies every finite piece of a theory, then you can find a structure that satisfies the whole theory. A key implication of the compactness theorem is that we cannot axiomatize finiteness in first-order logic. This is a fundamental limitation of first-order logic. The Löwenheim-Skolem theorems come in two flavors, downward and upward. The downward Löwenheim-Skolem theorem says that if a theory has an infinite model, then it has a countable model. This means we can always find a smaller structure that still satisfies the same theory. The upward Löwenheim-Skolem theorem states that if a theory has models of arbitrarily large finite size, then it has models of every infinite cardinality. This means that we cannot control the cardinality of infinite models in first-order logic. A complete theory is one that leaves no statement undecided. For every sentence phi, either T satisfies phi or T satisfies not phi. There are no undecidable sentences. A decidable theory is one for which there exists an algorithm to determine if any given sentence is provable. Presburger arithmetic is an example of a decidable theory. A type is a complete set of formulas describing an element. It's a maximal consistent collection of properties that serve as a blueprint for elements in a structure. Ultraproducts are constructions that combine many structures into one. Represented as the product of a sub I divided by U, they serve as tools for building new models with desired properties. Model theory has key applications in various areas of algebra, including field theory, group theory, ring theory, and Galois theory. For example, consider real closed fields where every positive element has a square root and every odd-degree polynomial has a root. This characterizes the real numbers algebraically. Some core techniques in model theory include elimination, which is quantifier removal, transfer, which is property preservation, construction, which is building models, and classification, which is structure analysis. The power of model theory lies in its ability to transform algebraic problems into logical questions, bridging the gap between syntax and semantics. It offers logic as a universal language. Model theory has connections to various fields, including set theory, topology, geometry, and computer science. The vision of model theory is to understand mathematics through the lens of logic. Model theory reveals the deep unity between algebraic structures and logical reasoning. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.